Thanks very much. We can move on to our discussion session. Let's see if we have any questions online first. Sherry, is there any questions online?
Nope, no questions online, but if anyone out there has any, please feel free to put those in the chat.
Yep, go ahead.
There's been a fair bit of discussion about autonomy, and I agree with everybody. I think this is certainly the wave of the future, but we've got a bit of a cultural issue with respect to NASA, because NASA is taking a very conservative approach, for good reasons, over the years. So everything from servicing satellites in Earth orbit, basically every step has to be supervised, to rovers on Mars, and now I think that's pretty much the same way with the plan for Viper. So how do we break that paradigm? Because I think all you guys have presented some great ideas, some good way to go, but if we don't get over that hump of the risk aversion with NASA, it's going to be tough for them to, to accept and fund these missions. I'd like to hear some thoughts.
Well, I certainly agree that there is, a certain amount of aversion to saying full autonomy, and you'll notice that I couched most of my slides with a human-in-the-loop focus. I was really focusing on people are making these decisions, but truly we want to advance to the point where we can just land a rover and it will complete the entire mission autonomously and take care of a lot of these optimization problems on its own. To answer the question of how can we break that paradigm, I think we need successful demonstrations. And so we have our baseline mission, which we must complete, and then our extended mission. And I think after we have completed our baseline science goals, that would be a good time to start sort of stretching our legs on autonomy. In my case, that would be setting those waypoints further and further and further apart and pushing the limits of, what we can demonstrate is possible.
Yeah, Dave Blewett, Johns Hopkins Applied Physics Lab. I think, with the low-cost missions like PRISM, it's a good opportunity to just, have a higher risk tolerance and to test out some of these things.
That's why Viper's flexibility to try it. Oh, sorry. Yeah, Viper's a bit of a disappointment because not really given the flexibility to try it out. Now these other CLPS missions, that will happen, but the NASA mission, Viper, is not have that flexibility.
Yeah, I'll just comment. I'm a PI of the Lunar Vertex PRISM mission. We have a lunar outpost rover on our mission, but the CP-11 lander is also going to carry a tech demo from the Jet Propulsion Lab, in which there's going to be 4 rovers autonomously cooperating. So, CLPS again provides an opportunity for tech demonstrations like that can help to advance these things.
Yeah, and I agree with that. When your rover costs, $2 billion, $3 billion like the ones on Mars, or it costs a few $100 million like a Viper might, you're basically you want to be risk averse, right? You don't want the rover to drive itself into a crater and destroy solar panels and end the mission, right? So you want some risk aversion. But when you start using smaller rovers, cheaper rovers, then they're more expendable. So you can actually try to demonstrate technologies. I want to bring to mind Deep Space 2 many years ago. Basically, went off to prove a bunch of technologies. Well, one of them was to automatically target an asteroid that was flying by and acquire imaging as it passed by. So it passed by, but we never got any of the images because it missed completely. So if that had been an actual science mission and they had relied entirely on automation, it would have been a disaster. That being said, like you said, the progress of automation can be incremental. For example, what we described here of the autonomous science rover is the main difference between what the rover did and what the people and the scientists did was select the traverse. They select the traverse for intrinsically different reasons, right? The scientists select traverse for what seems interesting mineralogically or geologically. The rover selects waypoints on the basis of uncertainty. It seeks to minimize uncertainty. So those two different things are basically how they select traverse. Now, if you're on a mission where you have to respond quickly, where do we go next on the basis of what you discovered here? Oh, wait, but the scientists are still analyzing the data. We have to wait for them to finish. At that point, the rover automation can take charge to decide the traverse so the science can continue going to important targets while the scientists are still analyzing the data. So it's an incremental thing, but in that case, you don't need to trust the rover in terms of how it's going to conduct this traverse, just where it's going to go.
Eldar, we have a couple comments on the chat. So Kaizad wants to say, just to echo, I agree that initial technology demonstrations in flight will be key. And we also have to showcase approaches towards verification and validation, managing uncertainty, and safeguards for mission critical applications. And then we have a question from Kayla Shang online, who says, similarly to the question just asked, are there any added risks to these autonomous rovers or robots versus human controlled? For example, with pilots and airplanes, a lot of work has gone into determining the exact balance of autonomy versus human control. Have there been any investigations or probabilities with mission halting issues for human controlled versus autonomous?
Who is this question for again?
It was not addressed to anyone, and she just said it's open to anyone that's present.
Cricket's out here. No one has any answer.
Hello, I'm Connor Westcott from Florida Space Institute. Although I didn't present, I do have my education in artificial intelligence. So a big issue with something like this is AI works in a black box situation. Don't let any AI researcher ever tell you that they know what they're doing. It's an art, it's a mystic. We really don't know what's going on, why they think the way they do. We are trying to figure out how these models do think the way they do, but that's a very hard sell at this point. Is it either has to be all controlled by the rover or kind of all controlled by the human. There isn't really a good in between yet, because from what we've seen so far is having interactions between a human and a full autonomous system, they typically rarely agree on how to solve the problem, even if they come to the same conclusion. Because the rover or the AI system is going to see things in a very non-human-esque way because it just sees the pure data, whereas a human is going to be being driven by kind of a lot more heuristics and cured human knowledge. So it's a hard balance to put there, if that makes sense.
Hi, Kezad here. Just to maybe provide one answer to Kayla's question in the chat. I guess that depends on the risk profile of how the autonomy is being used. So if you compare tying in a perception pipeline to managing data and identifying the right time to downlink data, but there's no real articulation of any hardware, that's typically less risky than if you were to use that perception and AI pipeline to control the rover autonomously or control the robotic arm autonomously. So I guess it would be interesting to see what mission halting scenarios could come up. That seems like a good basis for future experiments. Could be done tying different levels of autonomy for what the tasks are.
Hi there, Zach Morris, Howard University, NASA Goddard. A quick question for Michael, way back at the beginning of the session. I really loved your talk about the mixed reality mission control room. I was curious if your current design allows for multiple users to collaborate in the virtual environment, potentially from, if they're physically in different locations, could they collaborate in the same virtual space to act on the same mission?
Oh yeah, so I'm really happy you brought that up. That is one of the selling points actually for this type of interface. Actually, Jack Burns talked about this earlier in his presentation, where we envision this virtual control room to also act as a virtual hub where researchers can come together from across the country or even the world and collaborate to make these decisions to better control these robotic assets. So definitely, yes, this is I guess a threefold benefit to this type of system. We have a virtual space where we can see both third and first person perspectives from the robot, and we can also bring in virtual avatars of other researchers into the same place, similar to how maybe the Mission Control Center at JPL works. We can move that to a digital space. So yes, thank you for bringing that up. That is definitely something that's on our minds.
Awesome. Thank you.
Thank you.
I guess I have one question for Kaizad. Are you still there? All right. So one of your metrics was a science return. Most of the things that were being performed were basically, identification of lithological identification. So on what basis were you assessing science return?
It's a good question. I don't think I'm the best person to answer it. I believe there was a survey-based system tied to some of the specific science objectives that the science team had come up with. And I think it could be good to have one of my colleagues on the call to speak more about how the metrics were, how the data was matched to the metrics for those objectives. Sorry, I couldn't really answer the question.
Anybody else online have any questions?
I don't see any other questions online.
All right. Well, 4:40 is when we break, and it's 4:39. So I guess we can call it a break now. And oh, there's one more question. Go ahead.
Yeah, actually, for you, Eldar. So you said that for the autonomous system, the scientists came to the same conclusion, but I'm kind of interested to see how different the paths the rover took compared to the human directed versus the autonomous directed version. Was there a lot of difference in the paths, or did they kind of take a general same trajectory?
The paths were completely different. Unfortunately, I don't have I have the data on the Google Drive. I can show you later.
All right.
But none of the waypoints were even remotely close. The scientists, if you saw the first 2 points, where basically one was on the north, one on the south, and they kind of went on a rather broad zigzagging pattern there, or kind of clockwise kind of pattern, whereas the rover just beeline to the west and then kind of stayed around there for a while, and then basically beeline to the last waypoint. The only similarities were dictated basically the first and last waypoints were the first waypoint where the science team started, and the last waypoint was as far as they got. In their original plan they had 16 waypoints, but they only made it to 8 waypoints. So we told the rover, okay, you're only allowed to do 8 waypoints to be able to do a one-to-one comparison with what the science team did.
All right.
But yeah, the paths were entirely different.
All right. Thank you.
And it's again because the scientists are interested in things that look interesting. If you do a spectral mineralogical map, places where you have hotspots, right? You do a photogeological map, different geological units. The rover doesn't care about those things, doesn't even understand those things. It just cares about uncertainty. So it's dictated entirely on minimizing uncertainty. All right, well, if there's nothing else, I guess we can call it. Thanks, this was very productive, actually.
Thanks, everyone.